Okay, this video is part 2 of lecture notes 8.1 and 8.2. Just to kind of recap what we did on the first part. Well, we built our confidence intervals, and we talked about the basic idea that a confidence interval is essentially, just a quick recap again, you've got some funky distribution, or who knows what it looks like. We are trying to estimate perhaps the population mean. To do that, we're going to grab a sample, and we're going to, from our sample, that will allow us to find a sample mean, or a mean from our sample. And we hope that our sample mean is close to the population mean. In order to get a real idea of what the population mean is, we add some standard deviations and subtract some standard deviations, creating this interval that hopefully contains the parameter we're interested in, typically the population mean or population proportion. And so that's exactly what we've been doing, and we talked about, the general format is to create this interval, you're going to start with that point estimate, and again, you're going to add a certain number of standard deviations. Z star represents how many you add, and the standard deviation of your sample means, remember we learned in 7.1 that is the population standard deviation over the square root of n. So you're going to add that many standard deviations and subtract that many standard deviations, thus creating your window that, again, hopefully scoops up the actual parameter. And then where we left off at the end of the last video is we said that it's pretty common that we don't know this. If you're trying to find the population mean, it's pretty unlikely that you know the population standard deviation. Okay, it's more likely that you'll have to rely on the standard deviation from your sample. And if that happens, it changes things just a little bit. So we talked about how if we are not aware, or if we do not know what the population standard deviation is, an alternative, again, when constructing my confidence intervals, if you don't know what this guy is, an alternative is to use the standard deviation from our sample to approximate it. To use this guy instead, the standard deviation from our sample. The only problem is when we do that, this thing no longer follows my sample means no longer are strictly adhering to a normal distribution. It changes a little bit. And it's actually going to follow what we learned was called a t-distribution. Now, I mentioned in the last video, the only thing that this changes for us is, for the previous examples, we consulted a z-table to find this value. Now we just need to consult a t-table to find this value. So everything is literally identical, except we look at a different table to find the critical number there. How many of these standard deviations we're adding or subtracting from our point estimate of the mean. And I mentioned in the last video that just a little bit of the difference between a normal and a t-distribution. T-distribution is still symmetric, it's still unimodal, it's simply wider, it's more spread out, okay? And another thing that's a little unique about it is it depends on the degrees of freedom. That's what dictates how wide this thing is. The degrees of freedom are directly tied to your sample size. So when you're going to consult a table to find your special critical t-value, the first thing you have to know is, what are the degrees of freedom? It's always one less than your sample size. And in fact, we usually write the degrees of freedom as a little subscript. Okay, one less than the sample size. So if you want to build a t-interval, a one sample t-interval, again, you're going to start with your point estimate, and then you're going to add and subtract a bunch of standard deviations, and how many you add or subtract, that's based on the level of confidence and that you want, and the critical t-value that goes along with that we would find off a t-table, okay, or StatCrunch. All right. I think that's where we left off. So the first thing we're going to do is just figure out how to find these critical t numbers. Then we're going to more rigidly define how to do a confidence interval, and then we're going to get into 2 or 3 examples. Okay. So first things first here is they just say find the critical value needed to build a t-interval. So they're having us think about doing a confidence t-interval. And again, you would know to use t. The reason you would use t is if you knew the sample standard deviation as opposed to the population standard deviation. And I'll write a little summary of that at the end. So you know what? Let's just do it now, and maybe I'll do it again at the end. So one sample z interval, we would do that if we know the population standard deviation, right? So if we know sigma. If you don't know that, then you would use a one sample t interval to build a confidence interval, and this is if I don't know the population standard deviation, and if instead I'm having to use the sample standard deviation. So if you're having to use S, the sample standard deviation, then you are using a t-interval. If you know sigma, the population standard deviation, then go ahead and use a z-interval. Here you would consult a z-table, here you would consult a t-table, but the confidence interval itself is still going to be the same. Here it's going to be your sample mean plus or minus a bunch of standard deviations. Here it's going to be your sample mean plus or minus a bunch of standard deviations. Again, the difference is here I knew the population standard deviation. Here I did not, so I had to approximate it with the sample standard deviation. That then changes whether I'm using a z-score or a t-score, but the interval itself is the same. So all we got to make sure we can do now is make sure we could find those guys, because really this is sort of the more common scenario we run into. Like I said, it's weird if you're looking for the population mean, it's kind of weird to know the population standard deviation. More likely you don't. All right. So they're just saying find the critical value that you would need to use, the t star value, if you were trying to create an 80% confidence interval, okay, and you had a critical number, or your t critical value has 29 degrees of freedom. Now, if you remember, the degrees of freedom is always one less than your sample size. So another way they could have said this is they could have said that your sample size is 30, because one less than that would be 29, all right? Well, it's pretty darn similar in the sense that imagine that you're trying to block off the middle 80%. So 80% is blocked off in the middle. Doesn't that leave 10% in each arm, because it's got a total up to 100%. So 10% here, 10% here. Oops. Okay, that's the idea. Let's look at a t-table though. The t-table does operate a little differently. So let me pull up the t-table. It's also on Canvas under the file stats tables. So you'll have to scroll down through the z-tables and into a t-table. T distribution critical values. So these are your t star values. Now this is a little different because if you notice from the picture, these are actually telling me right area. Remember, the z-scores tell me left area. So that's one thing to pay attention to. The other thing that is a little different is with the z-scores, you have the z-scores on the edges and the probabilities in the middle, okay? The area under the curve in the middle. This is sort of the opposite of that. Down this column here, you have the degrees of freedom. So again, you got to first figure out the right place to go based on your degrees of freedom. And if you notice, it only goes to 30 and then it starts to skip and jump. You go to whatever's closest, okay? So you get as close as you can to the correct degrees of freedom. And then what these numbers up here is, this is the area. This is the probability that is right here, right of that particular t-score, and all of these are your t-scores. So let's try this problem. It said find the t-score that would be used if you were trying to have an 80% confidence interval. So the middle area is 80%, and we said each of these tails was 10%. Well, looking at how this table works, I'm basically trying to find where do I have an area of 10%. Well, here's the area of 10% right there. Right? There's area of 10%, all of these numbers. How do you decide which one of these critical t-scores to go with? That's based on your degrees of freedom. Remember, they said that I had 29 degrees of freedom. So what I need to do is I need to go down. First of all, let me highlight. This is the 10% area column. And I need to go down to where I have 29 degrees of freedom. It's right here. So if I just go over to where they meet, that is the critical t-score I should use. 1.311. That's how many standard deviations you're going to add and subtract from your sample mean. So it's a little different. It just takes a couple times using it to get your hand, or to get used to it. So let me flip back or go back to the notes real quick. Next page. So this was when 29 degrees of freedom. This was 1.311. Again, they're not having us do an interval. They're just having us find that t-score. So B, similar, it just says find the critical t-score or t-value for a 95% confidence interval with a sample size of 12. So if your sample size is 12, the critical t-score I'm looking at has 12 minus 1 degrees of freedom. In other words, it has 11 degrees of freedom. And if I want 95% confidence interval, I'm trying to block off 95%. Doesn't that leave a total of 5% combined in both of these two arms, because they have to add to 1? That means there's 0.25, 2.5, that would be 25. Let's try that again. Let's try that again. I'll just start over. 0.95, 5% between the two of these, so individually they each have 0.025 or 2.5% in each of those arms. Now when I go consult the T table, again, it tells me right area, so that's the right area I'm looking for. Because again, I don't have to worry about getting this number and this number, just like with the Z tables. By symmetry, they're the same, okay? Except one would be positive and one would be negative. I just want to know what is that number, and I'm always going to take a positive value. Because again, we're adding and subtracting those amounts, so it doesn't matter if you have a plus or a minus. They're going to end up, you're going to end up with the same results at the end of the day. So let's go to the T table again. Let's try this one again. So let's clear all this out. This time I'm trying to block off 95%. We said that leaves 0.025% in each of these arms, but I'm only worried about the upper right arm because again, my T table shows me right area. So I'm trying to track down an area of 0.025. Well, there it is. There's area of 0.025. So my t-score is coming out of this column, somewhere in there. And again, to figure out which one it is, you have to go to the correct number of degrees of freedom. Our sample size was 12. So remember, 12 minus 1 means 11 degrees of freedom. So 11 degrees of freedom, if I go over right there, I get a t-score of 2.201. that is the number of standard deviations that I'm going to add and subtract from the sample mean to create your confidence interval. So we're going to do one or two of these on the next page. And again, I know in the beginning this is overwhelming. I know that. However, I promise you, these get to be so routine that you could do these in your sleep. And that's really how you should practice them. You should practice them to the point where you just march right through them. Here is why these get very routine. It's for this exact, let me write down the answer here. Came up to 2.201, I believe. Here is why confidence intervals, and the same is going to be for hypothesis testing, is routine, or it's going to become routine. Because right now we've sort of been doing things kind of loosey-goosey, just not really with any rigid structure. Here is our rigid structure, okay? So you want to know these 5 steps, and every time you do a confidence interval, you will walk through these 5 steps, and I tell you, by the time you've done 3 or 4 of these things, you've got them down, okay? So first step is always define the parameter that you are estimating along with the level of confidence you're looking for. So again, the parameter we're estimating is usually the population mean or the population proportion. The confidence level, either they tell us or that's up to us to determine depending on what the problem is asking for. The next thing we're going to do is we're always going to state the statistical method we're going to use. Right now, all we've got are one sample z-test interval, or a one sample t-interval. Now, it is possible to have 2 sample test and intervals, and that's exactly what Chapter 10 is. Once we learn Chapter 8 and 9, Chapter 10 is the exact same thing, but for 2 samples. So very little changes, very little changes. We're going to do these same 5 steps over and over and over and over again. Okay. This step, checking the requirements, they state it as IRL, which stands for independent, random, and large, and we'll define that down below. But that's really important. That's basically to make sure that our statistics is on the up and up. And again, at the end of the day, we don't want people to argue with us or debate our answer. We want to have confidence in our answer, and that's how we do it. Step 4 is where you actually do the thing, where you actually create the confidence interval. That's step 4, right? So this is actually creating the interval, whether it's a z interval, in which case you're using population standard deviation, or if it's a t-interval. So in that case, you would be using the sample standard deviation. It just depends on what you have. Now those are both for means. We're not talking about proportions yet. That's the next section, because if you recall from Chapter 7.1, sample proportions are also normally distributed if you sample correctly. But their standard deviation is a little different, okay? So these are just for means. And then the very last thing is to basically interpret your findings. Write out the sentence or the conclusion sentence that says, here's my answer. So these 5 steps we will do every time. And the good thing about having those 5 rigid steps is it makes the problems easy. It's like you don't sit there and stare at a problem and wonder like, gosh, I don't know what to do. I don't know how to start it. You have exactly 5 steps to do. And if you do those 5 steps and each one is not that painful at all, you're done. You've got your interval or you've got your test. We're going to see the same thing for hypothesis tests in Chapter 9. It's nearly identical. Okay. Let's talk about this checking the requirements, IRL. Again, that stands for independent, random, and large enough. And so again, this is to make sure that our stats are on the up and up and that the answer at the end of the day, can't really have any major holes blown into it. People are going to have to trust what we find. So first of all, we like our sampling to be done independently, or just this idea that, remember pulling marbles out of a bag with replacement versus without replacement. We always hope that every time we sample something out that we are not affecting the next person to be sampled, okay? So a lot of times, though, the particular scenario is not independent, and we'll see that in a few examples, and we've already seen that a lot, that generally, in real life situations, we don't have independence. But what we rely on heavily, remember, is this 5% rule. Most of the time, that's what bails us out. As long as our sample size is small in comparison to the entire population, under 5%, then we can safely say that, well, even though our sample we may not be sampling independently, the difference in the numbers is going to be so minimal that we don't care. We're just going to take the easy way out and assume we are. We always should be making sure that we're using some sort of a simple random sample, some of the methods we talked about in Chapter 1. And we have to make sure that our sample size is ideally large enough. Because remember, the reason we need large enough, remember, why do we need the sample size to be at least 30? Because according to central limit theorem, that's what makes sure that the sample means are normal, right? Those guys will follow a normal distribution, right? Nice bell-shaped, predictable, easy to calculate curve if you sample sufficiently, if you get at least 30. Now that's not always going to happen, and so if you don't get a sample size of at least 30, that's okay. As long as your data looks sort of normal, meaning it looks kind of unimodal and symmetric, then it's probably going to be okay and safe to go ahead and check that box off and say, okay, maybe it's not normal, but at least it's not skewed, okay, that it's symmetric and unimodal. That should be sufficient for us. And we'll see some examples where we encounter this. The conclusion statement, the last step is to write up your findings. You can always just copy and paste this sentence and just input the things you want. Input your level of confidence, input the lower and upper parts of your confidence interval, and then contains the true mean or true proportion, whatever the heck it is you're looking for. Okay. When it comes time to do this on StatCrunch, I'll show you how to do this, but basically they're telling us here that if we want to use StatCrunch to estimate the mean, they tell us to go to t-stats, a t-distribution, because again, it's likely that we do not know the population standard deviation. And when it comes time to do 8.3 and we talk about finding the population proportions on StatCrunch, you'll go to proportion statistics. I'll show you where to find those. Okay, I think it's really important that we get our hands on some examples. And because I swear to you, by the time you've done the fourth example, or we've done them together, though we're only doing 2 right now, you are hit by this feeling of like, okay, this feels incredibly routine, and this feels exactly like the last one, just different numbers. And that's good. That's how it should feel, and that's how the rest of the course is going to feel. And that's why I say that this is sort of like the downhill stretch, or the easiest part of the course. Even though it's the most important and the heaviest material, it's so similar that you just feel like you're doing the same problem over and over and over again. And again, that's why traditionally people score really well on this exam, if we were having a traditional exam, because, like I said, it's so routine. So let's take a look at this example. And the first few of these there's a lot, it takes a while. So just hang in there. Let's get through this one, and then let's see that the next one we do feels identical. Okay, so this says, listed below are the speeds in miles per hour of cars measured from the 5 freeway near Santa Ana. This simple random sample was obtained at 3:30 p.m. on a weekday. The speed limit for the road is 65 miles per hour. So they sampled what looks like, 2, 4, 6, 8, 10, 12 cars. Let me just write that down. My sample size is 12. They sampled 12 cars. They somehow clocked their speed, and those were the speed of those 12 cars at 3:30 on a weekday on the 5 freeway. They were nice enough to go ahead and crunch these numbers for us, and they gave us the sample mean and the sample standard deviation. I mean, we could have plugged those in StatCrunch and asked it to do it for us, but they went ahead and did it, okay? construct or use the data to construct a 95% confidence interval for the mean speed. So again, let's just make sure we get what's going on. I don't know what the distribution of speed would look like on the freeway, okay? Probably maybe something sort of symmetrical. There's probably a very common speed that most cars are going, an average, and that's what we want to find. And there's not that many going faster, not that many going slower. They're all kind of bulked right around the average. So maybe something like that makes sense. Well, we took a sample, and here's where our sample maybe landed. Again, I put it less than the population mean. I don't know, I just guessed. But that's my sample, 60.67 miles per hour. We're going to construct an interval. So I'm going to add some standard deviations, subtract some standard deviations, and in the hopes that we captured the actual true average speed of all the cars on the 5 freeway at this time. Okay? So that's the idea. Our sample is probably close to the actual speed of all cars on the 5 freeway, but it could be less, could be more. We want to construct a window that hopefully captures the real answer. I want to write out the 5 steps for our confidence interval. These are the 5 steps we need to follow every time. Define the parameter and confidence level. 2 is state the method being used. 3 is check the requirements. Make sure our statistics are legit. Check independent, random, and large enough. 4, do the thing. Find the confidence interval. So that's where the actual calculation takes place. And then 5 is interpret or state your findings. Those are always our 5 steps, okay? Another reason people score well on these tests is because these are just problems are magnets for partial credit, okay? Because even if you screw up on one part of these, if you get 4 of the 5 parts right, then you did pretty damn good on that problem. Okay, so anyways, let's start with number 1. 1, define the parameter and confidence levels. So again, the parameter is the thing you're trying to learn about the population. They said find the mean speed. So we want the mean speed of all cars on the 5 at this time. The mean speed, we'll call it mu, of all cars on the 5 at 3:30-ish on a weekday. And we want that at a 95% level of confidence. Remember, what the confidence level means is we know that my interval is not always going to get that answer. Maybe my sample mean was too far to the right, so that when I construct my interval, I miss. I don't get it. That can happen. But if we're going with a 95% confidence level, that means that if you were to repeat this experiment 100 times, 95 of those times we would get it, and only 5 of those times we would miss. So it's pretty darn likely that the window we get is actually scooping up the answer. We feel very confident that the window we are going to make really probably contains the true answer. Okay, so I mentioned what I'm looking for and the confidence level. 2, I want to state the method being used. Remember, right now it's either a 1 sample Z interval or 1 sample T interval. To figure it out, you look at the type of standard deviation you have. I'm being forced to use the sample standard deviation. They did not tell me the standard deviation of all cars on the 5 freeway. That would be the population standard deviation. Since I don't know the population standard deviation, I only know the standard deviation for my sample, I'm using a T distribution, okay, or a T interval. So we're going to use a 1 sample T interval. Now, you might be thinking one sample, well, my sample size is 12. Yeah, but the idea is I only took one sample. I didn't take one sample there and another sample here. That would be an example of a two-sample method, which we'll get into in Chapter 10. So we only took one sample, and then we're basing our interval and our findings off of that. Okay. 3, check the requirements. So independent. Does one car have an impact on the other car? I say yeah. I think it inherently, these are not independent. If you're on the freeway and everyone around you is driving slow, it's probably going to force you to slow down just because you can't get around them, or it's just kind of following the herd. If everyone is speeding and driving fast, you're probably driving fast, okay? Or you might be influenced to drive a little faster. So I feel like each of these cars does potentially have an impact on the speed of their neighbor, okay? So that would mean that they are dependent on one another, okay? So they are not independent. But think of the 5% rule. We only have 12 cars. That is definitely, we can safely say that that's less than 5% of all cars on the 5 freeway near Santa Ana. So even though they may not be independent truly, we can treat the mathematics as though they are. So I'm going to say n equals 12 is less than 5% of all cars on the 5 at that time. So we can treat as independent. Okay. All right, how about random? Was a random sample used? I see that right here. It says this simple random sample was obtained at 3:30 p.m. Okay, so they don't elaborate, but they say yes, a simple random sample was used. Simple random sample was used. And then lastly, is our sample size large enough to say that the sample means would be approximately normal? And remember, for sample means, we want to know, is my sample size at least 30? And in this case, it's not, right? Here, my sample size is 12. That is not greater than or equal to 30. So you might be wanting to say it's not, well, you can say it's not large enough. It's not large enough to confidently say that those guys are going to be normally distributed. But if you remember back to 7.1, and we did those simulations on StatCrunch, I wasn't taking very large sample sizes, and we were still getting things to be fairly normal. And what it said in the notes a page back or so is that as long as your data from your sample appears to be somewhat normal looking, meaning unimodal and symmetric, then we're probably safe to move forward. And here they've graphed our data for us, and I'm assuming the reason is because of this thing right here. That data looks sort of normal. I mean, it looks unimodal and somewhat symmetric. Okay, so I think it's safe to move forward. So we'll say that we're not big enough, but our data is unimodal and symmetric. And again, the whole idea is this is at the end of the day, we don't want someone to be able to say, hey, well, I don't trust your answer because you weren't large enough. Your sample size wasn't large enough. Well, now we can turn around and say, yeah, it wasn't large enough, but look at the shape of the thing. It's behaving somewhat normal. It's unimodal and symmetric. So we still feel good about the results we're going to get. Okay, running out of room. Step 4, that's where you actually do the thing. Now we're actually going to do the confidence interval. Now remember, it's a one sample t interval. So I'm going to start with my point estimate, and I'm going to add a bunch of standard deviations. Now this critical t value has how many degrees of freedom? If the sample size is 12, there's 11 degrees of freedom. Okay? So, the sample mean they gave us, that's 60.67. This t-score, I don't know. We got to figure that out. Let's remember how to do that. I want 95% confidence, so I'm trying to block off the middle 95%. Didn't we say that leaves 2.5% on each arm? And I know my t-table tells me the right area. So what I need to do is consult my t-table, find where's the right area 2.5% with 11 degrees of freedom. And that'll tell me how many of these standard deviations I need to add left and right. So let me jump over to the t-table again and do that. Let's see, t-table here. So again, just a quick, what I'm looking for is I'm looking for this area here to be 0.025. Right, that's what I want. And again, I'm looking for a critical t-score with 11 degrees of freedom. So let's find the area of 0.025. There it is. There's 0.025 area. Again, which of those t-scores is it? Well, go to your degrees of freedom. That's this first column. 11 degrees of freedom was 2.201. Okay? So, back to the notes. Where was that stuff? Page 7. This is going to be, the t-score is going to be 2.201 standard deviations left or right. The standard deviation for these sample means is being approximated using this. The sample standard deviation was 4.08 over the square root of n, which is 12. Okay. Let me do this in one or two steps. Let me first crank out all these numbers, okay? I don't have that written down. Here's a calculator. Let's see. Let's see, square root of 12. Oops. So this all comes out to 2.592. Okay. So what I've got is I've got this interval. My estimate, my point estimate is 60.67. That's how fast everyone seemed to be going out of my sample, or that was the average speed of my sample. And now I'm going to add 2.592 to the right and subtract it to the left. And remember, we call this the margin of error. That's how much we're okay with being off. So let's see, 60. This is 63.262. And this is 58.078. Okay. So it looks like my window is going to be from 58.1 if I round it and up to 63.3. Okay. Man, I'm writing too big here. So then the last step, 5. The last step is to go ahead and interpret results. And so what we can say is we are 95% confident that the true mean speed of cars on the 5 freeway of all cars on the 5 at 3:30 p.m. on a weekday is between 58.1 miles per hour and 63.3 miles per hour. Okay, and that is our final statement there. I know in the beginning it feels like a lot of steps, but again, it's just going to become so routine and the same problem over and over and over and over again that you're going to be able to kind of do these in your sleep. So again, first step was we stated what we were looking for in the confidence level we wanted. We stated the method we're going to use. The third step is usually one of the more tedious. It's checking the requirements, making sure our stats are legit. The fourth step is where you actually create the interval, and the fifth step is where you write your findings down. Okay? And we rinse and repeat for every problem we're going to do. Even though the scenarios are completely different, it's the same process. So let's try the next example here. Next example says that a machine at a soft drink bottling factory is calibrated to dispense 12 ounces of cola into cans. A simple random sample of 35 cans is pulled from the line after being filled, and the contents are measured. The mean content of the 35 cans is 11.92 ounces, with a standard deviation of 0.085 ounces. Estimate the true mean contents of the cans being filled by this machine with 99% confidence. Okay, so I mean, this is a quality control problem, and you better believe they do this because they want to know how much Coke is going into the can. They don't want to be over, all right, and they don't want to be under enough for people to notice. So if the machines need to be calibrated, this is how they check them. They can't open all the Coke cans because then they ruin all their products. So they take some sort of a random sample, in this case a random sample of 35 cans. Okay. From those 35 cans, they found that the mean of that sample was 11.92 ounces, and the standard deviation of the sample was 0.085 ounces. So let me just write some of that down. N was 35. The sample from those 35 cans of Coke, there was 11.92 ounces on average, and the standard deviation from the sample is 0.085. Now, we don't know the standard deviation of all the Coke cans, right? Which makes sense that we wouldn't, because we don't even know the mean value of all the Coke cans. That's what we're trying to figure out. So we only know the standard deviation from our sample. Since we're working with a sample standard deviation, we're going to have to do a t interval, not a z interval. Okay. So again, hope everybody's got the idea. Who knows what the distribution of cola or Coke is in the cans, but there's some true mean. That's what we're trying to estimate, the true average of all the cans. What's the average amount of Coke in each can? We pulled a sample, and this is what we got. We're going to create a window around our sample that hopefully scoops up the true mean. All right, and we're going to have a very high level of confidence that we're doing that. Okay. I'm not going to rewrite them, but I'm going to go through those 5 steps right there. Always those same 5 steps. Okay. Estimate the true contents of the cans being filled by this machine with 99% level of confidence. So we're going to make a 99% confidence level. So 1, what do we want? We want the true mean contents of all the cans at the factory. And we want that at a 99% confidence level. Two, what method am I going to use? Again, at this point, it's either a z interval or a t interval. And because I have to use sample standard deviation, because we don't know it for the population, we're using a 1 sample t interval. Okay. 3, we need to check the requirements. Is our sample independent, random, and large enough? Again, and the whole idea here is make sure that we're doing good statistics. We don't want people to be able to argue with us at the end of the day. Independent. I don't even bother thinking about the situation. I mean, you could say that, yeah, well, if the machine gives 1 can of Coke 12.1 ounces, it's not going to say, well, I better take it easy on the next can and give them a little under. The machine just spits Coke out, right? So I would say it's independent. It's not like it's keeping track. It's equally likely to be anything around 12, you know. Again, we don't even have to go there. We pulled 35 cans. Presumably, there are thousands and thousands of cans at this factory. So 35 is definitely under 5%. And so we can almost always go with that 5% rule. Safe to assume 35 is less than 5%. Let's just say it this way, is less than 5% of all the cans. So we're not even going to debate whether it is independent. We're going to say it doesn't matter if I treat it as independent. So treat as independent. Okay. Was there randomness involved? Yep. It says that a simple random sample was involved. Didn't say what it was, and that's all right. It was probably something systematic, right? We said that works good for assembly lines, but yes, a simple random sample was used. So no one could complain about that at the end of the day. And was our sample size large enough to make these guys be normal? Remember, sample means will be normally distributed if you select a sample size of at least 30, which we did. So n, our sample size was 35. That's bigger than 30. So yes, our sample is large enough for the sample means to be approximately normal. Okay. All right. Step 4 is where you actually do the thing, where you actually create the confidence interval. So again, a t interval, you start with your point estimate, your sample mean. You're going to add and subtract a bunch of standard deviations. How many? That's based on your critical t-score. Now this would have 34 degrees of freedom to it, right? Because it's 1 less than your sample size. And the standard deviation of these sample means, well, it's really sigma over square root of n, but we're approximating sigma with s, the sample standard deviation, because that's all I have. I don't know what it is for the population. So the sample mean was 11.92. That was the average they found out of those 35 cans. My t-score I need to look up, so let's go look that up. Oh, but I got to know what area I'm looking for. So here I'm trying to block off 99%, which means these two arms together make up 1%, 0.01, which means each arm individually makes up 0.5% or 0.5%. So that makes this guy 0.005. Okay, that's what I'm looking for, that area to the right there. Okay, so let's see. Go to my t-table. And just redraw this and kind of, again, I think drawing them really helps. 99% in the middle. That leaves 1% combined here. So this is 0.5%, which would be 0.005, and this is 0.5%, 0.005. My t-table tells me right area, so I'm looking for that area, 0.005. Where is that? There it is. So my t-score is somewhere down on this list. How far down is based on the degrees of freedom. Now, I want 34 degrees of freedom, right? So let's see. Notice there's only a 30 and a 40. There is no 34, okay? So you got to decide, should I use this number? It's hard to see. Should I use this number or this number? Some people go to what's closest. I think it makes a little more sense to go to whichever one is going to make the window wider. So in other words, whatever's going to add or subtract more standard deviations left or right, because the wider your window is, the more likely you are to scoop up that answer, okay? Now let me think here. Is that going to actually kind of go against the 99% confidence interval? Hold on a second. Okay, yes, I've justified it in my head, because if you go further, if your window is wider, we are even more confident that I am scooping up the correct mean. So it's, hold on. Sorry, kid was playing with pots and pans and he scared himself. If we go with a larger t-score, that forces us to go further left and right. That makes the window wider, and therefore we are even more likely and more confident that we scooped up the right answer. So I am going to take the approach of going with whichever number is bigger. In this case, it's also the one closer to the number I have or what I'm looking for. But I'm going to use the t-score 2.75. Okay? All right. If you're using StatCrunch, it will give you a more accurate number. Okay? It'll shoot in between those and tell you a better number. And some t-tables, too, have more breakdown, more degrees of freedom. This is just the one I found. Okay, so anyways, 2.75 is my t-score. My sample standard deviation was 0.085 over the square root of n, which was 35. So again, let me kind of figure out what that is. That's my margin of error. That's how much I'm allowing myself to be off of the mean by. So let's crank that number out. The margin of error is 0.395. So my window that I'm going to hope contains the actual amount of cola in the can. Well, my sample sample mean was this. This is what we found. When I add on the margin of error, I'm up to 12.3. Let me make sure I did that right, because it's not matching the number I had. Oh, but when I did it, I used StatCrunch, so that could totally be it. Let me just one more time make sure my margin of error is right. Ah, no. Wait a minute. That time I definitely typed it in wrong. Sorry guys, hold on one second. Let's insert a division symbol there. Now let's see. Oh yeah, this is wrong. This is 0.0395, not 0.395. 0.0395 is what all that comes out to. So when I add that on, I get 11.96 if I round it. And here I get 11.88. So we are 99% certain that the true amount of Coke in each can is between those two numbers. It's actually less than 12 ounces. We're getting robbed a little bit here. So the last thing, state our conclusion. We are 99% confident. Oops, what the heck is this thing doing over here? That the true mean amount of cola in each can is between 11.88 ounces and 11.96 ounces. So their machines are off a little bit. I doubt they'll fix them because no one's going to know, and that way they're saving a little money. Okay. I guarantee, though, if it was on the other side of it, right, if they were a little above 12 ounces like they're advertising, then they'd probably need to, or they would probably choose to recalibrate the machines. Okay, one more page to go. So let's take a look at that. Okay, the last thing here is just one formula that's going to talk about, we've talked about margin of error. We've got our point estimate, and we're going to add and subtract some standard deviations, and how much we add or subtract, we say that's our margin of error. And it could be the case that we have a predetermined margin of error that we are okay with. So sometimes we do this from the sense that, okay, I've got a level of confidence I want. Other times I just kind of want to say, like, all right, I'm okay with, I want to be within, half an ounce of the true amount of Coke in the can, or something like that. So we know that the margin of error here, well, it consists of your t-score, right, times your standard deviation of your sample means, right? So in other words, what I'm trying to make the point is that it is controlled by your sample size. It's determined by your sample size. So the larger the sample size, that makes this denominator bigger, which makes this overall fraction smaller, which makes the overall margin of error smaller. Bigger sample size, smaller margin of error. Okay, so if you've got a predetermined margin of error that you're okay with, you then need to figure out, well, what should my sample size be to get that to happen? Do I need to look at 50 cans of Coke? Do I need to look at 100 cans of Coke? That's going to, the number of your sample size will have an impact on your margin of error. So what this last little formula here does, and honestly, we're not going to use this a ton in the course, but there's a little bit in the homework, so we'll go through it right now. It allows you to have a predetermined margin of error, and based on that, you can determine how big should your sample be. Okay, that's the whole idea of this formula we're going to see. So let's see, what does it say? The margin of error is how much we're willing to be off on our estimate. Yep, right, because that's up to how much we could be off by. It comes after the plus or minus part of our confidence interval, right? Yeah, we learned that. So they're just calling it E, right? Error is equal to this. That's what we just said is our margin of error. Now here's the idea. We want to, before we collect our data, we want to determine what N is, right? I need to figure out what N is before I collect the data, meaning if is all happening before I collect the data, I also won't know S. I won't know the standard deviation from my sample because I haven't sampled yet, because I'm not even sure how many things I need in my sample. We're trying to figure that out. So although we're going to end up, doing a t interval, again, the vast majority of the time, for this formula, we're actually going to go back to relying on a z-score. Okay, because technically, I'm just going to have to guess. I'm going to have to make my best educated guess at what the population standard deviation is. Okay, and using that best guess, we will be able to calculate the margin or the sample size that gives us the margin of error we're okay with. All right, so let's see where this formula comes from. So all we do is we take our error formula that they gave us right up there, and I'm just going to leave off the n-1 just to kind of keep it a little more succinct. All right, but that's the margin of error, right? Okay. Again, there's technically n-1 degrees of freedom here. Well, I just want to solve this thing for n. That's what I'm trying to do. I'm trying to get a formula for n, the sample size. So the first thing I'm going to do is I'm going to get it out of the denominator. I'm going to multiply both sides by the square root of n. That way I could say they're gone over here. and I get the square root of n times e, my error, is equal to my critical t value times s, the standard deviation. I can then divide by the error to move it to the other side, and I get the square root of n, my sample size, is my critical t-score times the sample standard deviation over the error that I'm okay with. And the last thing I'm going to do to solve for n is I want to get rid of this square root, so I'll do that by squaring both sides. And I'm left with n itself is equal to my critical t-score times the sample standard deviation over the error I'm okay with, all of that being squared. Now again, I haven't sampled yet, so I do not know what this is. I don't know what the standard deviation for my sample is because I haven't taken a sample yet. This all would take place before you sample because you're first really trying to figure out what should my sample size be. So because of that idea there, we switch from sample standard deviation to our best guess at what the population standard deviation is. And because I'm talking about population standard deviation, I'm no longer using a t-score, I'm back to using a z-score, right? Because z goes along with the population parameter squared. Now n should either be equal to this number or bigger, all right? It's always, you always round up, let's just say that. Always round up, okay? Because by taking a larger sample size is going to make a smaller window, which is going to be even less error, okay? So if we were okay with being off by half an ounce of the true mean number of ounces in a can of Coke, by taking a larger number of cans than we find from this formula, we're actually going to have less error, and it's going to be like 0.4 is what we'll be within, let's just say. So if you're okay with being half an ounce off, then we're totally fine being 0.4 ounces off. Okay, so I hope that made sense. Ultimately, know how to use the formula, know how to plug the thing in to find n. And so that's like what this next example is going to highlight. Okay, here this says that an IQ test is designed so that the mean is 100 and the standard deviation is 16 for the population of normal adults. So they gave me the sample mean, the population mean, and the population standard deviation. Okay, so we didn't have to guess this, they gave me that. And the population mean I actually don't need, I'm just writing it down. Find the sample size necessary, so we're looking for n, to estimate the mean IQ score of statistics students such that it can be said with 99% confidence, my confidence level is 99%, that the sample mean is within 4 IQ points of the true mean. That's your error. That's how much you're willing to be off by, 4 IQ points. All right. So, looking at my formula, the sample size I need to take has to be greater than or equal to this particular critical number times sigma, the population standard deviation, over the error I'm okay with, and all squared. Well, the error I'm okay with is 4 IQ points. The population standard deviation is 16. Now this critical z-score is the z-score I would find from a 99% confidence interval. And so we find that just like how we did earlier. I'm trying to block off the middle 0.99%. That leaves 1% combined in these two arms, which means there's 0.005 here and 0.005 here. Now remember, your z-tables tell you left area. So I would go consult the z-table that has the negative z values, because this z-score is left of the middle, so it's going to be negative. And I would find an area close to 0.005. Let's just do it. I was going to say, this is one of those numbers that they tell you to memorize If I remember correctly, it's like 2.5 or something. So let's go find it. Let's look at the z-tables. Okay, here's my z-score. I want this area to be 0.005. Okay, so I got to find that area somewhere in here. Remember, the z-tables show the area inside the table and the scores outside. So again, I went to the negative z-table because the z-score I'm looking for is left of the mean, so it'll be negative. 0.005 is in between these two. So it would be in between, let's see, negative 2.5 and in between it would be in between negative 2.57 and negative 2.58. So I'm going to split it down the middle and say it's negative 2.575. That's halfway in between 57 and 58. Okay? There's my z-score I'm going to use. So I need a little more room. 2.575. Okay, so let me crank all that into the calculator, hopefully right. 2.575 times 16 divided by 4, all squared. I get 106.09. Now we are talking about people here, right? Statistics students. You can't grab 106.09 statistics students. So you always round up. So we should sample at least 107 stats students. To get an estimate for mu to be within 4 points. Again, the idea is you've got your, now IQ scores, they're normally distributed. So there's some mean, and they tell us that it's 100, that is the population mean. But again, when I sample, I know that my sample won't be 100. It'll be a little less or a little more than 100. And so what we're saying is we want to make sure that we are within 4 points. So we want our interval to be within from 96 to 104 because that's 4 points above and 4 points below that mean. So that's the window we want, right? Because it said we have a margin of error, or I guess they just use E, of 4. So we need to sample at least 107 students to ensure that my interval that I create is going to be within 4 units of the mean. All right? Which actually, it doesn't have to be like how I drew this because remember my sample could be, I kind of drew it like centered right on the mean. It doesn't have to be that. It could be a little left or right. Okay. This was a long section. This ended up being a long video, and so was part 1 of the video. Take your time and rewatch it as many times as you need. Do not get discouraged or overwhelmed. I promise you, confidence intervals will become very, very smooth for you. And I think by the time we start looking at 8.3, 8.3 is the same thing, but it's for proportions, not means. It's the same exact process. The only thing that's different is the central limit theorem in chapter 7.1 says that for proportions, your standard deviation isn't this anymore. That's for means, right? For proportions, the theorem says that your standard deviation is this. But the 5 steps of the confidence interval are the same. The only thing that's going to differ is how I find my confidence interval. That's the formula for the confidence interval for a proportion, and that's all 8.3 is, right? This is what 8.3 is. So it's nothing new except a different way to find standard deviation. So 8.3 will go a lot faster, and I think it'll feel a lot smoother. All right, so hang in there. Keep up all the good hard work.